Hello, welcome back to Cinderella Math. Today I'm going to be doing quite a large, so buckle in, grab a snack, a large study guide that was given to me by one of my tutoring students, who is currently in like the very beginning of pre-calc. So I would call this like a pre-calc what you need to know going into like that first month of pre-calc. So if you're in Algebra 2 finishing up, this might be a nice review. And if you're headed into pre-calc, a nice review as well. So kind of like an late Algebra 2, early pre-calc level is where I'm going to put this. Um, yeah, I mean, of course, anybody's welcome to watch, but that's about the level here. I have the blank copy and I have the key. I'll probably bounce back and forth. I've also gone ahead and pulled up Desmos if you want to pull that up as well, or if you have another graphing calculator or just regular calculator, feel free to grab that. It's long. I think it's like 10 pages. So again, buckle in and we'll get started with transformations, which is one of my least favorite topics. I'm not that good at it, but we all have our good topics and our tricky topics. So if we're looking here at number one, they're just asking what did they do to it? Well, this was the parent. They're not asking this, but it's good to identify it. The parent function was the cubic. So it looks like they've done two things. They have -7, and see how that's with the x. That's going to be a horizontal shift of right 7. So you would think if you're on the x-axis and you went -7, you think that would take you to the left, but he lies. If it's with your x, it lies. All right, so that's one of the transformations. And then we have this negation and it's inside the parentheses. So the negation itself is being cubed. So when the negation is taking on the function on the inside, if you will, that is a reflection over the y-axis. When it's on the outside, so if the negative would have been here, see how that negative is not taking on the cubed in the pink example? That is a reflection over x. But when it is taking on the cube or the parent, if you will, it is a reflection over y. All right, I'm going to do number 2, and then I can go to Desmos and kind of prove both of those. So again, on number 2, they didn't ask the parent, but it's good to identify it. It is the square root function. So they did a whole bunch to this guy here. The order that you write these doesn't really matter. As long as you get them all, it's fine. See how the negative's on the outside? That's going to be a reflection over the x-axis. I'm going to leave that 1/3 alone. That's the hardest part for me. See how the 5 is with the x, so he lies, and that's going to be your horizontal shift. Since it's a +5, do the opposite of what you would think. So again, if you're here at 0, you think +5 would take you to the right. This is actually going to take you to the left. Okay, because he lies. And see that -8, how it's hanging off the end? That's going to be your vertical shift, and that does what you think it would do. So that's going to take you down 8. So vertical shift down 8. Okay. And then when you have a multiplication factor on the inside, so this 1/3, see how it's inside with the x, that is a horizontal dilation, and you do the reciprocal of it. So that's going to be a horizontal stretch, I believe, by 3. You do the reciprocal. So that was 1/3. I did 3. Okay, that's the trickiest one. I'm going to actually pop to the answer key, see if I got that right. Yes. Okay. And then if you're allowed a graphing calculator, number 1, the parent was x cubed. I will take off this writing in a second. And the new one, okay, let me take off writing. There. So the original is red and the transformation is blue. Let me take off the -7 for a second. There's just the reflection over y. And then I'm going to put in the -7, and we should see the blue one scoot to the right 7 units. Boom. So number 1 certainly was right. Here's number 2. Here's the parent. And then we negated it. So here you're going to see the reflection over x. We did +5, right? So that's going to take us left 5, boop. And then outside of it was a -8. So you should see this guy going down 8. Let me zoom out so we can see that. There he is. So we've reflected left 5, down 8. And then I'm going to add a 1/3 in here. And so this should get horizontally stretched. So it should be like 3 times as fat. Yeah. That is hard to see. Let me take that. Oh, let me take that out. There he is. Looking at the blue one there. Green is the parent. And there it is. That's hard to see. Kind of just have to know that one. But there we go. I'm coming down to number 3. Some of these already have answers on them, by the way, because it was from a student. It's a scan. So we'll just wipe those out and start it fresh. Write the equation of a log function. Okay, so the parent is log x. It didn't say a base, so just assume base, 10, right? Because you know if there's nothing here, it's a 10. So we're just going to assume that. They want a horizontal shrink by a 1/7, a reflection over x, and down 9. Okay, so I think our new function, all right, reflection over x, so a negative in front. Down 9 will be -9 right there. So check, check. And the shrink by horizontal, shrink by 1/7. Horizontal means we do the reciprocal and we put it with x. So x and 7, because we're doing the reciprocal. And that's just always the rule with horizontal, shrink, or stretch, or dilation, if you will. Okay, I'll check both 3 and 4 at the same time. So looking at 4, write the equation of a cube root function. So the parent was cube root x. Okay, they want a horizontal stretch by a factor of 6 and scooch it to the right. Okay, so our new function to the right is going to be x minus 6 because that lies. So remember up here, this is your vertical one. That one tells the truth and it's not with x. The right, the horizontal, oops, that should be a 3. The right lies. The left and right lies. Or the horizontal translation lies. There we go. And then stretch by a factor of 6 horizontal. So again, we have to do the reciprocal of 6. So 1/6 on the inside. 1/6 on the inside. Okay, I'm going to check those. Yep. Yep. All right. I won't take those to Desmos, but you're welcome to if you'd like. All right, use the graph below. What is the equation of the transformed cubic function? So let's see if my student was right here. Um, okay, so I think ignore this line right here. I think my student was just using that. Or maybe I wrote on this paper when my student was in my home. All right, let's see. So you kind of have to just know your functions, right? Your function families, we have linear, we have quadratic. So this is x squared, cubic, right? We have square root. We have cube root. Oops, this one's square root. This one's cube root. We have absolute value. So this one to me looks like a cube, cubic. Oh, duh, it says so right here. I don't read. It's a cubic. So, but we messed with it. We have transformed the cubic. So you need to know what the, if you're not allowed a graphing calculator, you need to know what the original cubic looks like. It hits at the origin and it kind of makes a snake. That is the parent of x cubed. So look at ours. It is flipped. The snake is like this way. So it has done a reflection over the y-axis. But then if it was just that, it would still hit it at the origin. This has got his little flip point up 1. So it's also gone up 1. Okay, so from the parent, which was x cubed, up 1. So that's going to be a plus 1 off the back. And a reflection over y is going to be negative x cubed. Yeah? Because y goes with the x. Let's check it. Oh, well, not quite. The plus 1 is right. And then it must also have been stretched. See, that's hard to see with the naked eye. It really is. So again, ignore this line. Let's just jot down, if it's just x cubed, right? If you plug in 0, you get 0. If you plug in 1, you get 1. If you plug in -1, you get -1. If you plug in 2, you get 8. If you plug in -2, you get -8. That's the original, right? Okay, obviously that's a rough graph, but something like that. That should have more of a hitch to it, but it's fine. So, okay. If we look at ours, if this was just negated and up 1, then all the y values (1, 1) would then be -1, 2, right? But ours is -1, 1, 2, 3, 4. You can't even tell. See, I'm not good at these. Ugh. Ignore that. This is the answer key's got -5 x cubed plus 1. So I certainly agree with the plus 1 because it should be, the belly button kind of should be right there and it's up 1. I agree with the negative because it got flipped or reflected. But that seeing the 5 in there is hard. Let's look over here. So here's x cubed. There's the parent. And here's the supposed answer for ours. There. Like, how can we tell that? I mean, so the black, the parent, is going up slightly more gentle, I would say, than the red. But how do you know that's 5, you know? Let's generate a chart on this one. Actually, let's do it on both. Let's generate a chart. That's what I was trying to do. Okay. See, you can't even. So on the original, it was -1, 1. Excuse me, -1, -1. But now on the new, it's -1, 6. Can we even fully see that on ours? -1, 1, 2, 3, 4, 5, 6. I guess you could buy that. Okay. And so the 6 is really up 1. So before the up 1, it was 5. So it was really -1, 5, but then it went up 1. Okay, let's see if we can see that on another point. Let me come back to Desmos. So like originally, we were 1, 1. That's on the parent, so that's on the black. On the new, the red, we're at -1, -4. Okay, let's see if we can even see that on our paper. So 1, -4. 1, 1, 2, 3. Okay, I guess I buy that. So again, really, that was because of the 5. It was supposed to be 1, -5. But we went up 1, which took it to 4. Okay, I buy the 5, but that's just very hard to figure out. Ugh. Yeah, sorry, I don't think I explained that well. I guess when it comes down to it, if it was just So here's the original again. Still ignore this. Okay, if it was just negate it and plus 1, this one doesn't actually help you all that much. Oops. Never mind. I don't think I can explain that one. I'm sorry. I tried. All right. So again, we'll just white out anything that's filled in. Certainly that's an absolute value, right? Anything that makes a V is going to be an absolute value. So we were told to graph it as well. Okay, the parent absolute value is f of x equals absolute value of x. All right, we've got two transformations. We're going up 1, so a vertical shift of up 1. And we're going to do the reciprocal of that because it's inside. So that's going to be a horizontal. It's either a shrink or I guess it's a shrink of 1/2. So the original, I'm going to graph it in blue, starts at the origin, goes up 1 over 1, up 1 over 1. That's the original absolute value. So ours is definitely going to go up 1 from there, but then with the shrink or stretch, whatever we're going to call it, I think either would be fine. I kind of have to plug in some points. So I'm plugging in some points here. Let's plug in 0. That would be 1. Okay, so I'm going to graph this in black. Let's plug in 1. That would be 3. Let's plug in 2. That would be 5. All right, let's do -1. That would be 3. And -2 would be 5. There we go. So I think I would call it a shrink. See how the black, which is the new one, got shrunken from the blue. Yeah. Now, some people can probably do that without having to do a little chart, but for me, the chart helps me get it right. So I'll pop to the key there. And of course, we could go to Desmos to see this. Yeah, it looks good. Yep. Okay, let's go here. Use the graph of f of x shown to the right to draw the following transformed graph. All right, these are hard because you don't have like a rule. That's like a weird graph, right? So let's see. That is, use the graph of f of x. Okay, this is the original. This guy right here. We're going to really, I would have put the original on the left, but it's fine. We're going to do this, the transformed. So what transformations happened? Well, this lies because he's with your x, so that's going to actually take us right 4. And this is going to reflect, because it's with the x, it's in the parentheses, reflect over y-axis. Okay, so I think we do the reflection first. So 0, 0 would stay 0, 0. This is 3, 3. So that's going to be 3, -3. Oh, reflect over y, sorry. So this is 3, 3. So that's going to be -3, 3. This is 6, 0. So that's going to be -6, 0. This is 9 down 1. So that's going to be -8, -9, up 1. And that's like, what, 11 up nothing? So that's going to be -11 up nothing. So that, I think, would be the answer if it was just the reflection. So that part's done. But now scoot everything right 4. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Oh, that's hard because I ran out of graph. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So circle, two, two. The blue is the answer. So what I was telling my student in my home is to write down the points and just do it. So that is another option. I think that would take longer, but it should work. So let me check with the key. I'm saying the blue is the answer. Oh, nope. Not quite. Wait, I don't think that answer's right. Right? Shouldn't the peak be up? Oh no, I'm wrong. I'm wrong. Let me try that again. One more time here. Ignore those points for a second. This stays. This. This. So this is 9 down 2, so this should be -9 down 2. I put that in the wrong spot. And 10, 11. Okay, that is just the reflection over y, and now I'm going to scoot it right 4. So here, oops, change colors. 1, 2, 3, 4, 4. Okay, this should be right. There we go. The blue is right now. Answer. Let me see. I think. Yes, that looks better. Boom. Okay, or that's just annoying, isn't it? What you could do, now again, this might take a little longer, and this is what I was kind of telling my student to do, but it will work. Just going to take a minute. Is write down the original points. Not all of them, but like a couple. So the same ones I just did when I was drawing. So we have 0, 0, we have 3, 3, we have 6, 0, and we have 9, -2, and we have 11, 0. Okay, and then flip them over the y. So the flip over the y, well, 0, 0 stays. When you flip over the y, your x negates, right? Because if you have a point here, you just flip it right there. So this would be -3, 3. Your x negates, your x negates, your x negates. So that's the flip over the y. And then this is, you need to go right 4. So now you're going to add 4 to all your x's. So that would be 4, 0. Add 4, so that would be 1, 3. Add 4, so that would be -2, 0. Add 4, so that would be -5, -2. Add 4, so that would be -7, 0. That is another way to do it, and now just graph those blue points. And this should be the same thing we just had. Boom. So whichever way made more sense to you. There we go. Can't really check that on Desmos because we have no function. Okay, state the parent, state the transformations, and write the transformed. The parent is also shown to help you. Okay. All right, well, the parent is certainly a quadratic. And certainly this vertex went left 5. So that's one of them. Left 5. And then certainly it's skinnier. But I can just never tell if it's a vertical. So I see my student wrote down there vertical stretch. How do we know? Let's again maybe jot down a couple points. So I know the original x squared, -1 goes to 1, 0 goes to 0, and 1 goes to 1. Okay. So basically, I know it goes up 1 over 1, up 1 over 1 for that first point from the vertex. Here, it looks like we're going up 1, 2, 3, 4, 5 over 1 over 1. So that leads me to think there's a 5 somewhere. Okay. So some stretch factor of a 5. But is it a horizontal or a vertical? So I'm going to ignore the left for a second. What if it just was a stretch? So if it was a horizontal by 5, it would be 1/5 x squared. If it's a vertical by 5, it would just be 5x squared. Like that, the 5 not in parentheses. Okay, so let's actually try that out. Let's plug in 1 into the horizontal. So if this is 1, 1/5 times 1 is a fifth. A fifth squared is a 25th. So this would be going up one, over one, basically up nothing. And then we'd scoot that left 5. I don't think that's right. Let's try the vertical one. If I plug in 1 squared is 1 times 5 is 5. So that'd be going over 1, up 1, 2, 3, 4, 5. And then we scoot that left. 1, 2, 3, 4, 5. Yep, that's the winner. So I kind of just had to do them both. So we have a vertical stretch of a factor of 5. Okay. There we go. I kind of just had a trial and error. Um, there's probably a better way to do that, but hey, it worked. So now our function, let me explain that. That is right, I think. The function, well, left 5, we know it's going to be x plus 5 squared. The plus 5, because again, he lies. And then we're going to put the 5 on the outside for the vertical stretch. No parentheses on him. He's not not with the x. The horizontal would be, but this one was vertical. Ooh, that's hard. Checking. Oops, I did not mean to do that. Yep, looks good. Third page. Draw a graph showing the parent function and the transform function on the same graph, listing at least 3 points for each. State the parent. Okay, well, here's the transformed. The parent is just 3 to the x. So let's go ahead, get that done. If you plug in 0, anything to the 0 is 1. If you plug in 1, 3 to the first is 3. I would plug in 2, but 3 squared is 9, and that would be off the graph. So I'm going to do -1. 3 to the -1 is 1 over 3 to the first, which is a third. So -1 up a third. Okay, so there's the original function, kind of your standard exponential function. Okay, that's the parent. Transformations, lies. So that's going to take us left 1. And since that's not in the parentheses, it's kind of out by itself, I think we're just going to say vertical stretch by 2. We don't do the reciprocal on the verticals. Okay, and then let's just do some points. If we plug in 0 into that one, 2 times 3 to the 0 plus 1, that would be 3 to the first, which is 3, times 2, which is 6. Put in 1. So that would be 2 times 3 to the 1 plus 1. So that'd be 3 squared times 2. That's 18. So it would be off the chart. Let's do -1. So that would be, let me kind of erase this. 3, no, 2 times 3, -1 plus 1. So that would be 2 times 3 to the 0. Anything to the 0 is 1. 2 times 1 is 2. And I'm going to add -2 right here. So that's 2 times 3 to the -2 plus 1. So that'd be 2 times 3 to the -1. We already did 3 to the -1. It's a third. So this would be 2 times a third. So 2/3. So left 2, up not quite 1. So that's going to be moving up way faster because of the 2. That's what that stretch is going to do to you. All right, you could go to Desmos and check that one out if you, oh, did I move them left? I didn't move them left. Nope, sorry. All the points on the blue move left 1. So the x needs to go subtract 1. So this will be -2, this will be -1, this will be 0, this will be -3. Okay, just scoot them all left 1. So left 1, left 1, left 1, left 1. There we go. The green is the answer. I forgot to scoot left. I think you always stretch first, then scoot, yeah? Boop. There. Wait, no. I didn't need to scoot left because I just plugged it in the function. No, nope. Sorry, it's getting late. I'm sorry. The blue is fine. I'm losing it. Blue is good. I didn't. No, you're good. Let me look at the answer. Losing my mind. Yeah, it's fine. Yep. Okay. Finally, we do not have to graph here. I mean, you could, but you don't need to. That is a reciprocal function. So how do I know? The parent, they didn't ask this, but they could have. The parent, well, they actually kind of did, is 1 over x. So it is called the reciprocal. Because isn't just straight up x, that's the linear, right? That's just a line. This is the flip of that, the reciprocal. So if they asked the transformations, this would be down 3, and this one would be left 2. They didn't, but they could have. And that's actually going to help us to know that. So, a couple ways we could do this one. Let me kind of, I know there's some answers on there. It's okay. We'll still go over it. So, reciprocal is actually what should be here, not rational. Reciprocal. All right. So, if you kind of just know, or if you're allowed to use a graphing calculator, the reciprocal function kind of looks like 2 bowls, if you will, or 2 L's, like that. That is the parent, 1 over x. And if you think about it, if it's, you cannot have 0, right? Because you can't do 1 over 0. 1 over 1 would be 1. If you plug in 2, that would be a half. If you plug in 3, that would be a quarter. So see how it just levels off? 2 up a half, 3 up a quarter, 4 up a fourth. And then if you did negatives, 1 over -1 is -1. 1 over -2 would be -half. And then -third, -fourth. Okay, that's the parent. But ours went down 3 and left 2. So we have a vertical asymptote right now of 0, but go left 2. So our vertical asymptote would be x equals -2. Okay, and we have a horizontal asymptote right now on this picture of y equals 0. That's where it's leveling off. But this -3 would scoot everything down 3. 1, 2, 3. So that would be our new y asymptote. Okay, so that's where these two answers have come from. But that's if you knew the graph. If you didn't, and again, this one should say reciprocal, the vertical asymptote, you take the bottom and set to 0. That's where that one comes from. The horizontal asymptote, if you just had this equation right here, take off the -3. If you remember from Algebra 2, and maybe you are in Algebra 2, so bear with, the power of the top, which is technically x0, so the power of the top is 0. The power of the bottom, this is technically x to the first, is 1. When the bottom is bigger than the top, so I call these the pigs because often the top is called p of x, so that's why I call it the pigs, and the bottom is often called q of x. I call these the queens. When there are more queens, they rule fairly. So if it was just this function, they're going to rule right down the middle at y equals 0. But it wasn't just this function. It then had a -3. So this would drop, the ruling fairly would drop down 3 to be -3. So that's how you can kind of do it if you didn't want to look at a graph. Okay. So now if we were to actually graph this, we'd have a vertical at -2, horizontal at -3. And then we would still have our kind of weird shapes. So the domain can be any x in the whole world except for that vertical asymptote. We just can't do -2. So it's x such that x cannot be -2. Or if you need to write it in negative interval notation, you can do -infinity until you get to -2, and you can do -2 to infinity. You just can't actually do -2. And the range, any y value is possible except for where this horizontal asymptote is. So y such that y cannot be -3, or if you need to do it in interval notation, you can go from -infinity until -3 and -3 to infinity. You just can't hit -3. End behavior, pretty much have to look at a graph for this on this one. If you take your little guy, walk him to the right, he would level off at -3. So as x goes to the right, the function goes to -3. Actually, you don't need the graph. It's just going to be the horizontal asymptote. So if you have this, you don't really need the graph. And then if you walk the little guy to the left, he'll also just level off at -3. Okay, there we go. I like that one because we didn't have to actually transform it all that much. Checking that one. Oh, I call this the reciprocal function. Okay, never mind. Rational it is. I think they both count. I think different teachers call them different things. It's fine. Everything else was fine. All right, here they just want the domain and range. So again, we could graph this. And if you took that approach, the parent is just root x. So if you know what that parent function looks like, it starts at the origin and gently to the right. But this one, it took it left, nope, right 2, bump, bump, and up 3. 1, 2, 3. So there would be the starting point or the end point, and gently to the right. So looking at the red one, the domain on the x starts at 2, and I'm doing a solid because it does touch and goes forever to the right. And the range, the y value, start at 3. I'm doing solid because it does touch and goes forever up. So that's kind of the graphical way to do that. What if you didn't want to do a graph? It's fine. You don't have to. This is a square root function, and square roots can only input positives, and we're not talking about i's. You can kind of ignore those for a second. So we know x minus 2 has got to be positive, and positives are bigger than 0. It could equal 0, so we will put the equal. Solve. So x has to be bigger or equal to 2. That's the domain. In in interval form, that means you start at 2 and go bigger. And again, I'm doing a bracket because we have the equal. Okay, so what's the smallest this is going to be? Well, the smallest that could be is square root 0, because again, we can't do negatives. No i's. We're throwing out i's. If that's square root 0, that's just 0. And then you still have plus 3. So that would be 3. That is the smallest output. And then they could go bigger from there. So the range, the smallest it's going to be is 3. So y is going to be bigger or equal to 3, which is this in interval notation. So you can kind of think about it algebraically, which was the green, or you can think about it graphically, which was the red. Next page. We did this page. I might have scanned it wrong. Yep, let's scooch that. Scooch, 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 scooch. There we go. Use the graph below to answer the following questions. Okay. I'm going to get these first. So minimum is a low bump. That's kind of hard to tell, really, but is it right there? No, it's more like right there. Huh. Use interval. So I would say that's like negative half, -12. That's like a guess though. And then these are our high bumps. That one we can do. And that one, 215. Again, that's kind of a guess. All right. And now I'm going to just work this whole thing backward. This means where is your function less than 0? That means where is your function negative? So that's just where it's under the x-axis. So here, 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 and then back here. So I'm assuming we can assume arrows. So this would be your very left, so -infinity, Go, 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 go. Stop, because it can't equal 0. So -2, stop. Go, 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 go. 1, stop. Go, 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 forever. And again, solved everywhere because we can't equal. So the next one up is, where is your function positive or 0? So where is it above the x-axis or actually touching? So here, 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 here. So -2 and, oh, so we'll do hard bracket on that because it does have the equal. And 1 to 3. Hard brackets because it does have the equal. So right there it does equal 0, so that's okay. Okay. Increasing, decreasing. You're going to pretend you're on a roller coaster and you're going to start on your left. So I'm kind of going to do these both at the same time. So right here on your left, up, 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 stop. So that's increasing because I said up from -infinity, the left, until -2, always soft. Get back on your roller coaster. Down, 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 stop. And we said before that that was like -1/2. So from like -2 to -1/2. All right, back on the roller coaster. Up, 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 stop. So and -1/2 to around 2, always looking at x values. Down, 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 forever. So and from about 2 to forever. Now, some of those were like guesstimates. Okay, so instead of like 2, it's like 2.25. I mean, good enough. Good enough. It's close enough. It's fine. That's picky. You can hardly tell, you know? It's close enough. I'm gonna leave it. All right. In my opinion, the rest of this is about to get a lot more easier. Find the slope of the line. You need to know your slope formula. Second y minus first y over second x minus first x. x1, y1, x2, y2. So that's going to be 4 minus -2. Sometimes I draw a backward arrow. -1 minus 3. This turns to a plus. So this gives us 6 over -4, which is 3 over -2. I like to write the negative on top. It doesn't matter. Find the equation of the line. Still start with the slope, so same formula. I'm doing the second y minus the first over second x minus the first. That turns to plus, and that turns to positive. Okay, there's our slope, and now they want point slope, so that's y minus y1 equals x minus x1. You can pick either point. I will pick the first one. Again, pick either. Picking that one. So y minus 5, because that's my y1, equals slope, which we just found to be 1/4, x minus, this is my x1, -3 minus minus turns to plus. There's your point slope. You could use the other point. If you do, it would be y minus 4 equals 1/4 x plus 7. So either one of those browns are right. Okay, now slope intercept. I'm just going to take that brown and actually solve it out for y. So get y by itself. So let's distribute 1/4. So that would be 1/4 x plus 3/4 equals y minus 5. I'm going to add 5. 5 is 20/4, right? 20 over 4 is 5. So y equals 1/4 x plus 23/4. It's not the prettiest thing, but that's okay. That's your slope intercept. So you need 3 well, you had to do the slope, and then here's your point slope and your slope intercept. Draw a graph of the line with the following equation. Doop, boop. Okay. y plus 5 equals 3x minus 6. Let's minus 5. Oof, did I mess up? Because I'm getting y equals 3x minus 11, but we're not even going to go down 11 on there if we don't have room. Let me see, did I mess up? No, it's fine. Just teacher messed up, whoever made this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just pretend. And then the slope is 3 over 1. So up, 1, 2, 3, right 1. 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 Okay, that's not perfect because I had to like start outside of it, but it's fine. Or this is point slope, right? So this is y minus y1 equals mx minus x1. So our m is 3, slope. And a point on here, this is x1, but just 2, right? Because that's, see the minus? So this x1 is just 2. And this must have been minus minus. So it was y minus negative 5, and they turned it to a plus. So y1 is negative 5. So that is the point on there. So these are just always opposite of how they looked. The 2 looked negative, it's not. The 5 looked positive, it's not. We could just go to that point. So 1, 2, 1, 2, 3, 4. There it is. And then our slope is 3 over 1. Up 3 over 1, up 3 over 1, up 3 over 1. That would work too if you didn't want to get the slope intercept. Either way. Okay, cool. All right. All right, we have this point here, negative 6, 8. So if you think about it, where is it? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. What would be a line through that point that has a slope of 0? That's a horizontal line. So that would just be, that's y equals 8. And a line through that point with an undefined slope, that's a vertical line. That's x equals negative 6. Done. Okay, don't overthink that one. Write an equation for the line. Okay, parallel means they have the same slope. So we need to solve this one for y to get the slope. I'm going to move this over. So this is x equals 2/3 y plus 1. I'm going to minus the 1. And I want y by itself, so I'm going to times by 3/2, right? That's the reciprocal. 2/3 and 3/2 will cancel. Times this one by 3/2. So 3/2 x minus 3/2 equals y. So this is y equals mx plus b. This is the m. So the slope is 3/2. Okay. And parallel means they need to have the same slope. So right here, they want slope intercept. So y equals mx plus b. There's the slope. We're keeping it the same. The x is negative 2 and the y is 9. We need to find the b. So we have 9 equals 3/2 times negative 2. This would cancel. Negative 3 plus b, add 3, 12 is b. So final answer would be y equals mx plus b. This equation that I just put in the box is parallel to this one, and it hits this point. Okay, let's check that. And that's a geometry problem, knowing that parallel lines have the same slope. I mean, it's also an algebra problem because you had to solve for y and all that goodness. Yep, it's good. Okay, clearing that one. Pause me if you need to. Perpendicular to the line, blah, 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 blah. Hey, at least this one's solved for y. So this is slope. But perpendicular from geometry, the slopes are negative reciprocals. So our new slope, take that one, negate it. Well, it's already negative. So it's going to turn positive and flip it. So 3/5. Don't need that anymore. So now y equals mx plus b. This is our new slope. Again, perpendicular. This is from geometry. You flip and negate. The x, using this point up at the top, is -2. The y is 9. We don't know the b. So 9 equals -6/5. Don't go decimal. Plus b. Let's move this over. So 9 plus 6/5 equals b. 9 is 45 divided 5. There we go. So that's 51/5 is b. Final answer, y equals mx plus b. She's not pretty. That's okay. It doesn't have to be. Yep, he's good. All right, this graph shows distance. What is Frank's average rate of change between 3 and 5 hours? Okay, so average rate of change is slope. So 3 here, 5 here. Let's jot down those points. So it's 390 and 540. Slope those. Second y minus first y, second x minus first x. So that's -50/2, which is -25. So -25 miles per hour. He's getting closer to home. From this time, he must have been like visiting a friend or something, and then he started driving back home, stopped at a gas station, whatever. He's getting closer to home. Did you have to do it that way? No. You could have also just looked from here to here, and it looks like it's coming down, counting by tens. 10, 20, 30, 40, 50 over 1, 2. So down 50/2, which is this. Either way. And how did I know it was miles per hour? Y, X. Okay, in the year, okay. All right, in the year 1990, that many percentage of American men between 25 and 29 have never been married. In the year 2000, 51.7 have never been married. Use the number 10 to represent 1990. So this is really going to be 10. And the year 20 to represent 2000. So this one's really going to be 20. So let's write these points. We have 10. And let's turn this, bump, 0.452. We almost always will turn percents to decimals when we're working with them. And then 20, bump, 0.517. Okay, let's go ahead and slope it because they want the line. So second y minus first over second x minus first. Certainly the bottom's 10. I'm going to grab my calculator for the top. That's 0.065. And I'm dividing that by 10 in the calculator. And that's 0.0065. That's our slope. Okay, so now y equals mx plus b, because they said slope-intercept form. That's the slope. I'm going to use the first point. So the x is 10 and the y is 0.452. We don't know the b. So times this, that's going to be 0.065. Subtract. Using our calculator to do 0.452 minus 0.065. And that gives us a b of 0.387. So this answer, I know I'm down on the next part, but it would be y equals m, which was 0.0065, x plus b, which is 0.387. Use your function from part A to predict the percentage of marriage who's not been married in the year 2015. Okay, so if 1990 was 10, if 2000 was 20, 2010 would be 30, so 2015 would be 35, and that's our x. So do y equals 0.0065 times 35 plus 0.387. So just shoot that green right through the calculator. and that is y equals 0.6145, but they want the percentage, so go bump, bump. So we estimate that 61.445% of men in the year 2015 have not been married, men between this ages. On the answer key, it then pointed to this and said not true. But, statistics, they're not always right. All right, let me check all that. That looked like a hot mess, but really the calculator took care of the hard stuff. Let's check all that. Yep. Um, Wait, they got 0.65. Okay, I got the same answer as them. Oh, they did not change the percents. Um, that's fine. Mine is still right. Yeah, it's fine. So they just left it as percents, and you know how mine on the answer, it was 0.0061. No, it was 0.6145, and I had to go bump, bump. They just didn't have to do that because they just left it as percents. I almost always will change my percents to decimals, but it's fine. So please feel free to look at that. Zoom in if you need to. I'll zoom it in. It's the same. I just had it, mine got more decimally, but there you go. If you want to leave it percents, that's what it should look like. But my final answer on B was still right. It's fine. Not going to redo it. Even and odd functions. Okay, let me remind you of the definition. Even means they have y-axis symmetry. Like that. That's even. Odd has origin symmetry. Like that. If you could flip your paper 180 and it would look the same. Okay, algebraically though, we're not looking at the graph. You are going to replace x with negative x. F of x equals f of negative x if the function is even. So we'll go back to the even example. Right here, this is point AB. This is point negative AB. See how the x negated, but the y value stayed the same. That's an even. On an odd, so here's my odd example. This point here is AB, and this point here is negative A, negative B. So when you input negative x, it gives you the negation of the function. Okay, so input negative x. So this would be 3 negative x cubed plus 4 negative x. A negative cubed is a negative. So this would be 3 negative x cubed, and then this would be negative 4x. This negative will look better in front. So this is negative 3x cubed minus 4x. Okay, so it's certainly not even because evens will match the original. That does not match the original function. So even is out. To check odd, due to the negation of the original function. So go back to that original function, and I'm going to run a negative through the whole thing. That would be negative 3x cubed minus 4x. Yes, that matches. So since when we inputted negative x, we got the negation, this one is odd. Okay. Coming to B, input negative x. So this would be 3 negative x squared minus 2. A negative squared is positive. So this would just be 3x squared minus 2. That matches the original. That means it's even. That's the best you can get, is when it just matches the original, boom, even. And finally C, this would be negative x root 1 minus negative x squared. I'm coming down here. That'd be negative x root 1 minus a negative squared is positive. Right? So does that match the original? No, because x and negative x don't match. So it's not even. Let me negate the original. So wouldn't that just be negative x root 1 minus x squared? which would be odd, but I saw the answer key earlier and it was neither. So let's look. Let's put this one in Desmos. I agreed with A and B. Here's A, by the way. 3x cubed plus 4x. See how that has origin symmetry? If you flipped it upside down, it would look the same. And I don't remember B. Here's B. And that is y-axis symmetry. You could just cut it right down the y. And here's C. X square root 1 minus x. I would maybe argue, wouldn't that look the same if we flip it upside down? So that point is 1, 0. I think the teacher's wrong on that one. I think it's odd. That would look the same if you flip it, yeah? Here, let's put in what we had. Negative x. I think you're good. I think that is odd. I think the answer key is wrong. Yeah, this is odd. Okay, cool. And here, I'll bring back the work. See, that is the negation. So the black down here is what I got when I inputted negative x, and the red is the negation. So go back to my notes. If when you input, you get the negation, it's odd. So that's a mistake on the key there. This one is odd. If you flipped it upside down, it would look fine. Definitely not even. Okay. Piecewise functions. All right. So if you're less than 2, you're going to use this rule. And if you're 2 or more, you're going to use this one. Okay, so -1. So you can kind of think of it this, actually, let's do here. If you're 2 and less, use the red rule. If you're exactly 2 or more, use the blue rule. So -1 is here. He's in the red. So plug that into the red. 3 times -1 plus 4 would be 1. Answer. 2 is filled in with blue, so use the blue. So do 2 minus 1 squared minus 3. So that's 1 squared minus 3. That's 1 minus 3 is -2. Answer. 3 would be here. He's in the blue rule. So this would be 3 minus 1 squared minus 3. 2 squared minus 3. 4 minus 3, 1. Okay, and graph. Use pencil. The red one is just a line. It hits at 4. 1, 2, 3, 4. Slope is 3. Up 3 over 1. Down 3 over 1. Down 3 over 1. You don't have to do as many points as me. Slightly sketch that. You would be in pencil. Boom. Now we're going to erase some of it. Because look back at our number line. This is for 2, well, less than 2. So come 1, 2. So this would actually be like up here, yeah? Open dot, because we do not have the equal, and keep the left. So actually all of this would live because it's all to the left. If there was anything to the right, you would erase it. But because of the way this graph is, it's not. Okay, the next one, that is a quadratic. X minus 1 squared minus 3. Sorry, let me switch to blue. This one. The vertex would be 1, -3. Remember, this one lies. So we're going to come 1, 1, 2, 3. There's our vertex. And then we had this point already, 2, -2, because that was using the blue. And we had this point already, 3, 1. So see how that was up 1 over 1? So up 1 over 1. This was up 1, 2, 3, 4 over 2. 1, 2, 3, 4 over 2. And then gently with your pencil, there's your parabola. But that was only the rule for 2 and to the right. So come back on your thing. 1, 2, connect solid dot, because it does equal, and keep the right. So the light blue we're keeping, and I'm going to erase the dark blue. That's what that graph should look like, I think. Let's check the key. Mhm. Yep, looks good. Looks good. Let me unzoom that a little bit. Yep. Is it continuous? No. Let me put my graph back. Okay, that's not exactly in the right spot. Something like that. It's not continuous. You have to pick up your pencil. And where do you pick up your pencil? Right there at that open hole. And then you would jump down here. So it's not continuous at x equal 2. So no, discontinuity occurs at x equals 2. That's where we pick up our pencil. If you want to know if Desmos does these, they do. 3x plus 4. So you just type 3x plus 4. And then you use squiggly brackets, x is less than 2. There it is. And you can see it'll tell you where to stop off. It won't show the open dot though, which is annoying. And then the other one was what? X minus 1 squared minus 3. So do that. And then squiggly brackets, that was for x greater than or equal to 2. And there it is. And again, it won't show this. Well, it will show the solid dot actually. There he is. Okay. That's how you do it in Desmos. All right. Next page. What is the domain? Okay. So the x values, so this goes left forever. Keep going, keep going, keep going, keep going. This is solid, so that's fine. Jump. That's okay that it's open because it's covered by the solid. Solid, so that's okay that it's open because it's covered by the solid. I think the domain is everywhere because even though we had some opens, so it's not continuous, that's for sure. But even though we had opens, they were covered by the solids. All right, and range, how low does he go? 0. So we'll do solid because it does hit 0. And goes up to 1. But see here it keeps, you would think it would stop, but here it's all in between, so that's okay. Here we've got an open circle at 2, but that's okay because it's closed over here. Keep going, keep going, keep going, keep going. We have an open circle at 3, but that's fine because it's closed right there. And then this just goes up forever, and so does that. So I think it's 0 to forever. So again, we had some open areas, but they were closed off by another part. So again, you would think you'd have a mess up right here, but because this Y hits again right there, you're good. Same here, it hits. What intervals is it increasing, decreasing, or constant? Okay, start on your left and ride your roller coaster. So left, down, 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 stop. So from the left to 0, we are decreasing. Okay, get back on. Up, 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 up. So we are increasing from 0 to 1. Always soft parentheses on here. And you're looking at the x values. We are constant from 1 to 2 because you're just walking straight. And then back on up, 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 up forever. So increasing and 2 to forever. Okay, now they want us to write the equation. Okay. I'm not going to scroll down there to do it. I'll do it right here. So this is certainly a piecewise, 3 pieces. Put a big brace to hold all your pieces. All right. So this looks like the standard quadratic, yeah? Because if you plug in, if it's x squared, you plug in 0, you get 0. If you plug in 1, you get 1. If you plug in -1, you get 1. If you plug in -2, you get 4. Yeah. So that's just x squared. So it's x squared, and then that starts at 1 and goes left. So that's if x is less than or equal to 1. Why equal? Because it has the solid. Okay? For this flat little piece, that y value is just 3 if x is between 1 and 2, and we'll close the 2 because of the solid dot. And finally, we just have that linear piece. Okay. We would like to know the y-intercept of that. So let's find the slope up 1 over 1. So if we come down 1 over 1, down 1 over 1. Okay, that was the line before they like erased some of it. So it looks like it was hitting at 0, and the slope is 1. So this is y. Well, you don't have to do the y. So it's really y equals mx plus b. So it was y equals 1x plus 1. No, plus 0, because it was hitting at 0. And how'd I know? We just extended it using the slope. Don't need the 0, don't need the 1. So this is just x. If this starts at 2, so 2 and bigger to the right. So x is bigger than 2. No equal because of that open dot. Ooh, doggies. Let's see here. That was all fine. Back up to where it was constant. He has a solid bracket. I disagree with that, but okay. Everything else was fine. All right, we're talking about step functions. Patrick Henry volleyball team would like to buy shirts. Here's the price per shirt. So if the coach orders 30 shirts, how much money will each shirt cost? So down here on the x-axis is shirts. We're going to get 30. Do, 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 do. There, so 15. Okay, write an equation for this step function. I think I get cut off there. Okay, so f of x equals big bracket. Wish I had more room. Okay, I'm going to actually just come over here and white some stuff out. Okay, so if you buy from 0 to 20 shirts, it's going to cost 20 bucks per shirt. So it's just 20 when x is in between 0 and 20, and we will close that because of the solid dot. I'm not sure if the 0 needs closing or not, because I mean, you're not going to buy 0 shirts, right? You're going to at least buy 1 shirt. So I would leave it like that. Okay, the next step is at 15, and that's if you buy between 20 and 40. And we will close or put equal on the 40 because of the solid. Okay, so if you get more and more t-shirts, it's getting cheaper. So they'll only cost 10 bucks each if you order between 40 and 80. Close the 80 because of the solid dot. And if you're buying a whole bunch of shirts, maybe it's a fundraiser, you sold a bunch of shirts, amazing, good job. If you're getting more than 80, they're only going to cost 5 bucks each. That's a good deal. So 5 if you're doing x is greater than 80, not equal because of the open dot. All right, that should be your step function. I'm clearing and checking. Yep, that's fine. And they did not close the 0 because you're not going to order 0 shirts, right? That's silly. Okay, now let's graph a step function and determine domain and range. Okay, it says, I'm going to do this one in pink. to go to -5 if x is less than or equal to -1. Okay, so gonna come down 5. 1, 2, 3, 4, 5. If x is less than or equal -1. Okay, it says come to -3. I'll do this one in green if you're in between -1 and 3. So down, 1, 2, 3, open, and then go to 1, 2, 3, closed. And then it says come to 2 if x is bigger than 3. So up 2, open forever. And there you go. Okay, again, you could do that on Desmos. It won't show you the open dots, which is a little annoying, but you could do it. Yep, I think mine looked fine. Okay. Oh, domain and range. Sorry. Domain is all reals because the pink goes left forever, the blue goes right forever. This open dot could be a problem, but it's covered by that solid. And this open dot could be a problem, but it's covered by that solid. So domain is everything. Range, not everything. So range, the only three y values it hits is -5, -3, and 2. That's it. Let's see if that's how the teacher wrote that. They didn't. um, but yeah, that's what I would do. Alrighty. An archer's arrow follows a parabolic path. Da, 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 da. Sketch the graph. Okay. So this is A, B, C. Let's find the vertex by doing -b over 2a. So that's going to be -2 over 2 times -0.005. Okay. I'm just going to use my calculator for that. Okay, that came out to be 200. And so that's the x value of the vertex. And now plug that into the function. So do -0.005, 200 squared plus 2 times 200 plus 5. Go ahead, just run that right through the calculator. I got 205. So that's our y. So our vertex is 200, 205. Okay, so how far, the height is that, and the x, okay. The x is the arrow's horizontal distance, and the y is the height. Okay. So how far from the release did it reach its maximum? So let's just say this is the maximum. This graph is not to scale. That point right there is 200, 205. And you're going to shoot it out your arrow, something like that. Again, that graph is not to scale. How far from your release? So here you are. Actually, it won't be down here. Here you are. Whee! The x is the horizontal distance. So 200 feet from its release, it reached its maximum height of 205 feet. Why feet? Because it says so in the problem. Okay. And then the next part is find the horizontal distance that it travels before hitting the ground round to the nearest foot. Okay, so we want it to hit back down. So that's when the height is going to be 0. So right here. So if you had a graphing calculator, click. And I will show you how to do it on Desmos. But assuming you cannot use Desmos, I would go ahead and do quadratic formula. It's not going to be pretty, but let your calculator take care of the nastiness. Okay, hopefully you have quadratic formula memorized. If not, memorize it. It's -b plus or minus square root b squared minus 4ac all over 2a. So there's a, there's b, there's c. So we have -2 plus or minus square root, 2 squared is 4, minus 4 times that nasty fraction, or excuse me, decimal, times 5 over 2a. Okay, I like to do the bottom first. So that's -0.01. So I'm just going to erase that. Okay, then I do the discriminant, the under the radical in the calculator, but don't hit the radical. So just do 4, because that was 2 squared, minus 4 times negative 0.005 times 5. Okay, that's 4.1. So I'm going to put that under. All right, and now let's go ahead and take the square root of 4.1, and that's like 2.02. Okay, so I'm going to just erase 2.02. And now we need to do this problem twice. We need to do it with a plus and we need to do it with a minus. So do negative 2 plus 2.02, divide it by negative 0.01. So just doing that in my calculator, top first, divide bottom, and that's negative 2. And now I'll do the minus. So negative 2 minus. So negative 2 minus 2.02. And that's 402. Okay, this one makes a lot more sense because it's how many feet did it travel before smacking back down? You cannot travel negative 2 feet. I mean, I guess you could, but this one makes no sense. Okay, it's this one. This thing traveled 402 feet-ish, because we rounded that decimal, before smacking back down. That's the answer to the last problem. I'm just not going to scroll down. Okay, let me check. Yep. Did I get 205? I don't even remember. Yep. Yep, they're all right. Now, if you're allowed to use Desmos, you're going to do that. You're just going to type the function, which was negative 0.005x squared. I don't remember the rest. Plus 2x plus 1. Okay, you might have to zoom out. Find your vertex. There, 200 is the horizontal distance because that was the x. 205 was the max height. Boom. Click. 402 rounded was when it hit back the ground. That's how far it traveled before hitting back the ground, because the height is 0 when it hits the ground. Alrighty. Factoring. This one's going to be fast. This should honestly have been first. I factor these with the magic X. If you do another method, go for it. There's a 1. Multiply, add. 4, 3. So that's x plus 4, x plus 3. Done. There's a 1. 16, negative 8. What if you did negative 4 times negative 4? That multiplies right, that adds right. So you can write this one as x minus 4, or x minus 4 squared. Multiply, add. What if you had 6, spend 1? So this would be x plus 6, x minus 1, not done. When this is not a 1, he's a cheat. We multiply to cheat. You're going to divide to uncheat. 6 divide 2, well, that's 3. 1 divide 2, you're going to whip that up because that doesn't go in. So that's 2x minus 1. Answer. I see a GCF on number 5. 18, 21, and 30. We could get a 3. This has 3x, this has 2, this has 1. So we could take out 1 that they share in common. That will leave 6x squared, 7x minus 10. Now let's factor. 7. So multiply here, add here. What if you had 12, spend 5? Drop the 3x, he's there for the ride. X positive 12, x minus 5. He's not a 1, so he's a cheat. Divide 6, divide 6. Drop. 12 divided 6 is 2. 5 divided 6 is not pretty. Jwoop. Okay, I'm doing this very fast because it's by pre-calc. If you're in pre-calc or if you're latter stages algebra 2, this should be good. If you're using a different method, that's fine, but this should still be good. The next one, number 6, is a difference of squares. You just set up your 2 parentheses, take the square root, which is 7x. Take the square root, which is 10. Give 1 a plus, 1 a minus. Done. This one I see a GCF because they're both even. So we could take a 2, which would leave 4x squared minus 9y squared. Now that's a difference of square. Drop the 2. Set up your parentheses, take the square root, which is 2x. square root, which is 3y, give 1 a plus, 1 a minus. Factor the following quadratic. Okay. Multiply. 12 and 7. What if you had 4 and 3? That multiplies and that adds. So that's going to be x plus 4, x plus 3. But wait, this is not a 1, so he's a cheat. We multiply to cheat, divide to uncheat. So that's going to be x plus 1, and just leave it. Yeah, just leave x plus 3/4 because it doesn't say factor. It doesn't say tell the factors. It says find solutions. So you're going to go ahead and set those both to 0. So set this to 0. This would be -1. Set to 0. This would be -3/4. So you don't need to like get the factor all pretty. What does this mean? If you graph this parabola, it would have solutions at, that's horrible, but it would have two solutions at -3/4 and -1. You could check it on Desmos if you desire. I don't desire, but you could. Quadratic formula, we already did this one in the word problem. Oh my, okay. It does need to be set to 0. So 9, 11, and 12 are good. 10 we'll have to fix. A, B, C. Negative, I'm going to write it in the middle so I don't have to write it every time. Okay, so this would be -5. So that'd be 5 plus or minus 5 squared. So 25. Technically, it's -5 squared, but a negative squared is positive. Minus 4ac all over 2a. 2 times 3, 6. Using my calculator to do that inside. -107. We don't like that negative. We're going to pop that out and make it an I. So that's going to be 5 plus or minus I root 107 over 6. 107, that doesn't divide by 2, that doesn't divide by 3, doesn't divide by 4, not 5, not 6. I think it's prime. So I think you're good. Okay, I'll check it. Yep, he's good. All right. Coming over to 10, we're going to set this equal to 0. So move that over. Now we're ready. There's a 1. A, B, C. Negative, negative, B. So that would be positive 5 plus or minus 5 squared is 25. And again, I know it's negative, but -5 squared is also 25. Minus 4, A, C, all over 2A. 2 times 1, 2. Use your calculator, do the inside, 13. 13. Does that have any factors? No, it's prime. You're done. 5 plus or minus square root 13 over 2. Okay, coming to 11, it's already set to 0, so we can just start. A, there's a 1, B, C. So negative B plus or minus B squared, so 1 squared is 1, minus 4, A, C, all over 2A. 2 times 4, better known as 8. Calculator, 1 minus 4 times -6. That's 97. I think 97 is prime. Think you're done. Answer. If it's not prime, I kind of hope we get one. You break it down. Or if you can pull out a square root, you would. If you could simplify the radical, you would. Final one, there's a 1. A, B, C. Negative B plus or minus B squared, so 4 minus 4 AC all over 2A. Well, 2 times 1 is 2. Calculator for the inside. That's -24. Okay, we don't like the negative. Take it out, make it an I. Now 24 does break down, right? It's 4 times 6, which is 2 times 2, partner. 3 times 2. Now you didn't have to break it down that way. Other ways would have worked, but you should have come out with the same prime factorization. So we have -2 plus or minus 2, because when you have a partner, you get married and move out of the house. Don't forget the I. Root 3 times 2 is 6 all over 2. So that's where we're sitting there. I'm going to erase the red coming up into that area. You would think you're done, but you can divide by 2, you can divide by 2, you can divide by 2. Never mess with the guy in the house. So that's going to be -1 plus or minus 1i root 6 all over 1. Anything divide 1 is itself, so you don't need the all over 1, and you technically don't need the 1i. You could take that one off. Answer. Just checking all those. Yep, yep, yep. Good. Complete the square. Okay. Again, you do want it set to 0. All of these are, so that's great. And then you're going to move the constant over. You're going to do a blank on both sides. Only start this if there's a 1 in the x squared spot. This one does. Number 13, we're good. You're going to do some side work. Coming to my margin, you're going to take the middle number, chop it in half, and square. That goes in both blanks. This should factor nicely. What multiplies to 4 adds to 4, 2 times 2. So that's x plus 2 twice. That's why it's called complete the square. We're making a perfect square there. Take the square root because I don't want a square. Make sure on the other side you do a plus or minus because that's the rule. And move this in front. So that would subtract and be -2 plus or minus root 17. Okay, 14 is going to be way harder because of this 4 in front. We're still going to move this over. And now factor the 4 because this must be a 1 for this to start. Then we can do the blanks. So we pulled the GCF of 4 out of the left. Now we can do our side work. This one's not going to be fun. Take the middle number 1, cut it in half, which is a half, square. A half times a half is a quarter. 4 times a quarter is 1. So that's what goes on the other side because you have to keep the balance. Because if you distributed that 4, 4 times a quarter is 1. Drop the 4. This should factor nicely. What multiplies to a quarter adds to 1. A half times a half is a quarter and adds to 1. All right. Divide by 4. X plus a half squared equals 1. Take the root, take the root. So that's x plus a half equals plus or minus 1. Move that over, so x equals -1/2 plus minus 1. That's where we stopped on 13, but we can actually do this arithmetic. So do x equals -1/2 plus 1, x equals -1/2 minus 1. Well, 1 is 2 halves, so this -1 plus, so that's a half. This one is 2 halves, -1 minus, so that's -3 halves. Final answer here is 1/2 -3 halves. Okay, I'm going to pause for a second and let you get that down because I will clear for the bottom two. I'm going to check those. Yep, and yep. Bottom two, just pause me if you needed that. Rewind if you need to. 15 is not going to be bad because at least there's a 1. Go ahead and move that over. We can go right to the blank. Side work. Take the middle number, chop it in half, square it. Both blanks because we don't have to distribute anything. This one should factor nicely. Multiply to 16, add to -8. You owe me 4, you owe me 4. That would, yeah. So that's x minus 4 twice equals -2. Take the root, take the root. So that's x minus 4 equals I root 2. Don't forget your plus minus. Move this over. X is 4 plus minus I root 2. Answer. All right, and 16 is going to be ugly. Let's negate. No, go ahead and move that over. Okay, we need this to be a 1. So we're going to pull a -3. That'll be 1x squared. 6 divided -3 would be -2x. Now we can do the blanks. Side work, take the middle number, chop in half, square. That's going to be 1 here. If you distribute it back, that would be -3. So that's 11. This one should factor nicely. 1 and -2. Multiply to 1, add here. -1 times -1. There. Okay, that's sloppy. Let me fix it. Okay, divide by -3. So we have x minus 1 squared equals -11 thirds. I just always like the negative on top there. Root. So x minus 1 equals plus minus I root 11 thirds. Move this over. X equals 1 plus minus I root 11 thirds. Now, that's answer, but it's probably not because we're not really supposed to have fractions in the radical. So we should probably fix that. So x equals 1 plus minus I. And let's do it like this. Root 11 over root 3. And then to get the radical off the bottom, because it's just a rule that we're not really supposed to have one, times by that radical. So this would be 1 plus minus I root 33 over root 9, but root 9 is just 3. That's probably the answer. I'll check that. I gotta clear for a second. Yeah. That's fine. All right. I think that's it. Woohoo! Ah, that was long. Oh, no, it's not. Okay, never mind. One more page, I think. One more page. Yep. Okay, that was the end of the page, though. Yes. Okay, one more page. Put these in vertex form. So complete the square. Set it equal to 0. Move this over. That's a 1 in front, so we can go right to the blanks. Side work. 16 cut in half is 8. 8 squares, 64. You can go both blanks because we're not distributing. Factor 64 and 16. Multiply here, add here. 8 times 8. So that would be 8 twice. And that's -7. Move that back over. X plus 8 squared plus 7. That is our new function. And that is in vertex form. This one lies, this one tells the truth. So if you were to graph this, you go left 8, up 7, happy face, parabola, because this started with a 1. 1 is positive, you're having a positive day, smile. The axis of symmetry, they didn't ask, but if they did, it would be x equals -8. Always x equal because it's a vertical line. No x-intercepts because it's not going to hit. It's a happy face that's above there. And y-intercept's going to be somewhere here. Plug in 0 into the original. So that's 0 squared plus 16 times 0 plus 71. Well, this would cancel, and you get 71 over 0 up 71. All right, 18. Move this over. Pull the 2 on the left. 18 cut in half is 9. 9 squared is 81. 81 there. 2 times 81 is 162. So that's -8 there. This should factor as x plus 9 twice. Okay. And then just move the 8 back over. So this is our function. 2x plus 9 twice plus 8. Vertex, lies, truth. If they ask, the axis of symmetry would be x equals -9. If you were to graph that, happy face, because why? 2 is positive, you're having a positive day, smile. So we're not going to have any x-intercepts because it's never going to reach there. Plug in 0. This would be gone, this would be gone. You'd get 170 for the y-intercept. Okay, I'm going to check all that. Yes, you could check all that in Desmos. You couldn't check the axis of symmetry, but you could check everything else. Yep. Right. Now these are already in vertex form. So looking at 19, lies truth. So -4, 3, x equals -4. Oops, we got a graph. Let me zoom down actually. Let me try that again. -4, 3. Okay. X equals -4. And it's positive, so it's going to be a happy face. We're going to come up 1 over 1, 2, 3, 4. Up 1 over 1, 2, 3. A wide happy face. I kind of missed it, but it's okay. Okay. X-intercepts, none. You're not going to hit it. Y-intercepts, you need to plug in 0. So this would be 1/4 0 plus 4 squared plus 3. So this is 1/4 4 squared plus 3. So this is 1/4 times 16 plus 3. 4th is 16 is 4 plus 3 is 7. Well, that's certainly not what it looks like on mine. It's supposed to hit at 7. Okay, let me graph that again. Hmm. Okay, I'm gonna plug in just 1. So that's 5 squared. Ooh, no, that's not gonna work. Let me put in -4. Nope. I'm gonna put in -8. -8 plus 4 is -4. -4 squared is 16. 1/4 of 16 is 4 plus 3 is 7. Okay, -8, 7. There we go. Okay. All right, and this other one, I'll clear what's already in there. Okay. All right. Lies, truth. So that's 1/4, x equals 1. It's just always the x of the vertex. Okay. And it's a frowny. It says a negative beginning. You're having a negative day, so you're going to frown. So we will hit the x-axis. So let's get the y-intercept first. Let's go ahead and plug in 0. I know I've got part of the function covered up. That's annoying, isn't it? All right, let's plug in 0. So that's going to be -1/4, 0 minus 1 squared plus 4. So that's -1/4, -1 squared plus 4. That's -1/4, 1 plus 4. That's -1/4 plus 4. So that's like 3.75. So the y-intercept, when we put in 0, we got 3.75. The fraction would be 0, and this is really 16/4, so 15/4. That's probably a better answer. Put that for a y-intercept, 0, 15/4. So it's like 3, almost 4. So like here. Okay, to get the x-intercepts, we have to set this to 0. I'm going to cover up the previous problem. We're going to set to 0. So -1/4 x minus 1 squared plus 4 equals 0. Move that over. Times by the reciprocal, so that would be -4 over 1. Cancel, 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 cancel. Times by -4 over 1, which is just -4. So that's 16. Root, root. So that's 4. Don't forget your plus or minus. Move over. X equals 1 plus or minus 4. 1 plus 4 is 5. 1 minus 4 is -3. So 1, 2, 3, 4, 5. 1, 2, 3. Boom. 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 Intercepts 5 and -3. Or if you want them as points, over 5, up nothing, -3, nothing. Yes, you could use Desmos to check all that. Again, not the axis of symmetry so much, but the rest, yes. Checking. Yep, 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 yep. Good, good, good. Discriminant is, if you did the quadratic formula, it's what's under the thing. It's b squared minus 4ac, but not the square root of it. So a, b, c. So 36 minus 4 times -2 times -7. Just put that through your calculator. That's -20. When this is negative, you're going to have two imaginary roots. When it's positive, you're going to have two real roots. And when it's 0, you're going to have one real root. So ours was negative, two imaginary roots. Okay, that was so much. Woo. They put complex, same thing. Complex is imaginary. It's fine. Yep. All right. I'm sorry I kind of did bad toward the beginning of that. I'm not the best with the transformations, but I try my best. And sorry I got a little fuzzy there because it's like 10 o'clock at night, but I did it. Okay. I hope that was helpful. I hope someone watches this, and I hope you're having a good day. Bye-bye.